To develop the formula for the surface area of a surface of revolution, we consider a function f, or at least part of it, as x goes from a to b, and we rotate it about the x-axis, and the result is a three-dimensional object, but we're only considered with the two-dimensional surface area. Now, associated with the object here is a series of radii, and I've identified the radius at A and the radius at B, and we can see, of course, that the radius is the function height. In order to consider the entire surface area, what we do is we do what we did when we first saw integrals. We consider an incremental distance on the x-axis, call this delta x, and associated with that is a trapezoid. No, this isn't like the trapezoid rule, but there is a trapezoid. And when the trapezoid rotates around the x-axis, it produces what we call the frustum of a cone. So we can imagine that there used to be a cone here and the top has been chopped off. The frustum of a cone here has two radii, a lower radius, which I'll call R2, and an upper radius, which I'll call R1. And these correspond to these distances on the for the function value above the x-axis. And for this frustum, what we need is the surface area. If we can come up with the surface area for this frustum, then that's the surface area for one little trapezoid here that's being spun, and then add together a whole bunch of them. That's going to be the integral process that you're familiar with. Well, in order to come up with the surface area for the frustum of a cone, it would make sense to come up with the surface area of a cone, like a larger cone and a smaller cone. Subtract the smaller from the larger, we'll be left with the frustum. So we consider a cone of radius r that has the edge of the cone has a length of L. You may have thought we were going to go with height on that one, but no, we're going to consider the length of the edge. And what we're going to do is we're going to imagine that we are taking this cone and we're going to cut it along that line, and we're going to end up with a sector of a circle. Now we have a central angle here of theta, and as you can see, the circumference of the base of the cone here corresponds to the arc length of the circle. Over here in the cone, we can see that the circumference is equal to 2 pi r. Over here for the sector, we have a length of L that would correspond to the radius of the circle from which this sector comes. And for the sector, we have that the arc length is L times theta. Therefore, we can equate these two and say that 2 pi r is equal to L times theta. And so that theta is equal to 2 pi r over L. Now we have the angle in terms only of r and L. Remember, 2 pi are constants, or 2 and pi are constants. If we then consider the formula for the area of a sector, we have that it is 1/2 r squared theta. We have this handy expression for theta, which is 2 pi over L. So we end up with that the area is equal to 1/2. Now this is for the sector, so r squared is going to be L squared, and theta is 2 pi r over L. The L's divide out, and so the area of this sector, as the 2's divide out, is pi r L. The reason we care about the area of this sector is because that is the same as the area of this cone. Well, the surface area of the cone anyway. Now it would be worth our time to consider this frustum in terms of its side lengths L. We've got one edge here, a little itty bitty edge, which I'll do in blue, and I'm going to call that L, and it corresponds to, over here, the edge of the trapezoid that made the frustum in the first place. If we let p sub I minus 1 and p sub I be 2 points on the curve that give us this little L, then we can say that the distance between p sub I minus 1, and P sub I is equal to L. And here we're using the absolute value notation, but it denotes a distance. Now that L is just for the little edge of the frustum. Let's also refer to the length from the edge of that frustum to the top as simply L1. Then we have L1 corresponds to the ghost cone up here on the top, and R1 corresponds to the base radius of that ghost cone. R2 corresponds to the base radius of the entire cone, the frustum plus the ghost. And this edge here would then be L plus L1. Substituting for these, well, we can say that the area of the frustum is equal to the area of the larger cone minus the area of the little cone, which is the one that I just called the ghost cone. Now I've redrawn the two-dimensional version of the cone so that we can, so we can have it in front of us, and then we're going to use it in a couple of different ways. First off, we have the area of the larger cone, which is going to be pi r2 times the quantity of L1 plus L minus the area, the volume of the ghost cone, which is going to be pi r1 times L1. And I should say that that equals the area. Manipulating this equation just a little bit is going to give me that A is equal to pi times the quantity of LR2 plus L1 R2 minus R1. If you'd like, go ahead and pause to confirm that for yourself. Using similar triangles, we get that L1 over R1 for what I called the ghost cone is equal to L1 plus L over R2 for the large cone. Cross multiplying gives me L1 R2 is equal to R1 times the quantity of L1 plus L. Distributing on the right and then factoring out L1 will give me L1 times the quantity of R2 minus R1 is equal to LR1. The reason we care about that is because L1 times the quantity of R2 minus R1 is showing up in our expression for the area of our frustum, the surface area of our frustum. So putting that expression in place where we saw it in the area of the frustum will give us A is equal to pi times LR2 plus LR1. Again, that replaced the underlined quantity. Now, if we let R be the average of R1 and R2, then we have a formula that we can write. We can say that the area is equal to 2 pi RL, where the 2 here comes about to offset the 2 we got from considering the average. Now we've gotten a pretty good way with this formula here, but I need to put a period. The issue here is now we have an R and we have an L, but that didn't really have anything to do directly with the function that we're talking about, f. So let's consider how we can replace R and L. L is the distance between P I sub I minus 1 and P sub I along the curve. So we can write L as the distance from P sub I minus 1 to P sub I as the square root of 1 plus f prime of x sub I star squared delta x. This comes from the development of the arc length formula. You may be wondering now, well, where the heck did x sub I star come from? Well, the idea here is that x sub I star is an element in the ith subinterval. Then the function height here is going to be f of x sub I star. And that's going to be related to the radius of the frustum. How does that work out, you ask? If delta x gets really small, then the height at one end is about the same as the height at the other end. Let's see what I'm talking about. If delta x is really small, then these two heights come pretty close together. So they're about equal to each other, and we can express them as f of x sub I star. The idea here, of course, being that y sub I is f of x sub I, and y sub I minus 1 is f of x sub I minus 1. And as far as we're concerned, these represent R. So going back to our formula, we've got area is equal to 2 pi RL. Therefore, the area of the frustum becomes A sub I is approximated by 2 pi. R is f of x sub I star. L is the square root of 1 plus f of x sub I star, that's f prime of x sub I star, squared times delta x. So we're almost there. The surface area from A to B is then S is equal to the integral from A to B of 2 pi f of x times the square root of 1 plus f prime of x squared dx, where the square root times dx is our ds. This formula is for a surface of revolution about the x-axis. Another way to write this formula is S is equal to the integral from A to B of 2 pi y times the square root of 1 plus dy dx squared dx, where again the square root times dx is ds. If we happen to have x as a function of y, we would end up with the integral from c to d of 2 pi y times the square root of 1 plus dx dy squared dy, where again the square root times dy is ds. We developed that in a previous video. All of these would be for the surface of revolution, and the rotation is about the x-axis. And all of these are summarized as S is equal to the integral of 2 pi y ds. What helps me to remember all of these formulas is that if we take this little trapezoid and rotate it about the x-axis, then the circumference here would be 2 pi times the function height, right? So 2 pi y. And then the little frustum-y edge here is our ds. And I kind of think of that as 2 pi r h. It's kind of like a cylinder, except instead of vertical walls, we're using the arc length instead. If we are instead rotating about the y-axis, then S becomes the integral of 2 pi x ds. And the x would then be your distance from the y-axis, right? I really should put limits here. We'll say a to b here, and then c to d here. Sure. As far as ds is concerned, we use whichever form of ds is most convenient. And when I say whichever form is most convenient, what I mean is we consider whether we have a function of x or a function of y.